Hi everyone and welcome to Activity 32. Today we are going to start talking about vectors and using their magnitude as well as component forms, and then talking about some operations. So a vector is a mathematical quantity that has both a magnitude and a direction, and it's represented by what we call a directed line segment. So you have to have an arrow to show which direction your vector is going. So in this vector shown here, we see the tail, which is always your starting point, as well as that head, so we know what direction it is forming. That will always require an arrow. The magnitude of our vector is the overall length of the vector. So we see here this would be representative of the magnitude, aka the length. And then we have a vertical and a horizontal component to show how much we are moving right and left versus up and down. So A is the horizontal, the right or the left, positive right, negative left. B is up or down, positive up, negative down. Now to actually calculate the magnitude of the vector, we use those two components, A and B, and it essentially is some Pythagorean theorem then to get the overall length. Notice those absolute value bars around our vector V indicate that we want that magnitude, aka the length. Also, we will talk about equal vectors. We will say that vectors are equal if they have the exact same component form, aka the magnitude and the direction. So again, that's going to end up coming from same component form, A comma B. So we see here a couple examples of our vectors being drawn. One of them is being told that we start at 1, 2, that's the tail, and then the ending point, the head, is at 3, -2, so we could draw that in. Another thing that you might see is the word standard position. That just means that your starting point, your tail, is at the origin, and in this case, you are moving left 4 and up 3 units. So for these first examples, we have some vectors that we want to draw on the coordinate plane. For this first one, vector V, we are going to start at 2, -5. That is, and we are in standard position, excuse me. So when you're in standard position, really you're starting at 0, 0, and we are going to the right 2 and down 5. So our vector V would look like so. Our second one, vector U, has a tail at -4, -2. So here's our tail, and then the head is at -2, -2. So again, we're going to draw an arrow to indicate we started at the tail and we moved to the head. So this is going to end up being vector U. Our last one has a tail starting point at -1, 2. So there is our tail, and we are moving to the right 3 and up 3 from that value. So if we are moving to the right 1, 2, 3 units, and then up 1, 2, 3 units, our vector T would look like so, with that starting tail at -1, 2, and then the movement to the head, right 3, up 3. In example B on the next page, we see here some determination if our vectors are of equal length, and they are finding that by taking the head coordinates minus the tail coordinates if you don't have a picture to represent this. And again, they are going to only be equal if the component forms are the same. When they are not the same, as in what we see here, -3, -4 is not the same as -3, -5, so that's why these vectors were not equal. So if we look at this picture below, we are given 3 different vectors. The first ones we are given are V and U. And if we look at vector V, we are moving to the left 2, 4, 6 units, 8 units to the left, excuse me. So for vector V, and then we have a vertical component of 2, 4, up 6 units, because each unit's counting by 2. And then we have U. We are moving 2, 4, 6, 8 to the left, and then up 2, 4, 6 again. So we would say that yes, these are equal because our component forms are the exact same. They are equal. When we compare then u to t is moving to the left 2, 4, 6, up 2, 4, 6. So vector t's component form, we didn't go as far to the left. We went the same b component, however. So for u and t, we would say no, the component forms are not equal. Now, sometimes they are going to give us the values without a picture. Again, you want to take your head coordinates minus your tail coordinate pieces to find the overall movement for your vector. So for instance, we are starting at the tail and then we end at the head. So we're going to take the x value from the head, subtract away from it the x value from the tail, and then we're going to do the same things, head coordinate minus tail coordinate, and our overall movement then, remember, minus a negative is the same thing as saying plus, so we end up at 20, and then negative 15 minus 6 more is negative 21. And that's going to make sense as our final answer, because if I started at negative 8 and moved to 12, I went up went up 20 units, aka 20 units to the right. Or in this case, if I started at 6 and went to negative 15, I went down the 21. So that would make sense for our vector's direction. Now, we also can talk about then finding different magnitudes. So on this next question, we are giving a starting point, aka the tail, and then we are giving where it's moving to, aka that would be the head. So when we are looking for the component form of this situation, we would be taking, again, our head coordinate minus our tail coordinate for the x's, and then head coordinate minus tail coordinate for the y's to get parameter b. And in this case, we end up with 48, comma, negative 55 as our a and our b value. So when we see this movement, if we want the overall magnitude, aka the length of this vector, we are going to use the component form for this vector and our a and our b values that we found. And you could take a squared plus your b squared value and then square root that to find that overall length. Think back to what we talked about here with Pythagorean theorem to find basically the hypotenuse, if you want to think of it that way. So a reminder, when you type this in your calculators, make sure you are using parentheses, especially around this negative value, negative 55, to make sure that your calculator computes the order of operations correctly. You should have 73 as the length. Okay, now we also are going to look at, again, the meaning of equality here. Reminder, even though this would result in the same magnitude, our directions for vectors m and n are very different. Because think about, if I have vector m, and if I drew this in, I'd be going to the left 5 if this was even in standard position, up 4, and if I went to the right 5 and down 4, yes, these vectors are the same length, but they have different directions. So if your component forms are not equal, you cannot say these are equal. Now we move on to the next lesson, 32.2. We see on page 446 that we have two vectors being combined together. Our first vector, which is going to be vector u, starts in standard position, and it's going to the right 6 and up 8 if we go starting at that tail going towards the head. Again, our component form would be 6, 8. The second vector, in this case, we would call this one vector v, is starting at 6, 8 and moving to 18, 3. So for vector v, it is moving to the right 12 and down 5 units. What we're going to notice here is the resulting vector that kind of combines tail from our starting, original starting to the head of our ending is going to be the combination of this, where they went to the right 18 and up 3 units. And what we notice is, think about if we added these values together, 6 and 12 is 18, 8 minus 5 is 3, we are getting this third set of component forms as a result of adding vector u plus vector v. So what we notice is this is our vector operation of addition. So if you add tip to tail, whether we take vector v and move it to be tip to tail here, right? We see this resulting vector u plus v. Or what we can do is we can take vector u and again add it tip to tail here. We still get the same resulting vector through that vector addition. So what's happening each time is you essentially are adding your horizontal components, in this case 4 and -3. If we add those together, and then we would have 1 and 4. Add those together, our resulting vector would be 1, 5. Or if we look at the second example, we have -6 and 8. Add those together. Our y components, -5 plus -5. Add those together. Resulting vector to -10. Now what we are going to notice when it comes to this vector addition, it is not just because we add the vectors together, we still would always need to calculate new magnitudes. For instance, we're basically saying here that just because we have individual magnitudes of vector v and vector u, that's not going to necessarily be equal to the magnitude of u plus v each time. So you want to be careful to make sure you calculate your magnitudes individually. Now, in the idea of vector addition, is it commutative? So can you do u plus v or v plus u? The answer is yes, and we kind of showed that graphically over here when we were talking about tip to tail on these, because it does not matter, the same resulting vector will occur each time. All right, now our next operation that we are going to talk about is the additive inverse, aka if you negate your original vector. In this case, they were talking about vector w. So essentially what's going to happen is you want to think about, again, with the additive inverse, you're basically like you are negating, flipping the signs of your original. So if I want the additive inverse of vector w, aka negative w, this is actually going to flip the sign, so it's now +2, and -5 would be our resulting additive inverse. And if we look then, if we flip the page, if we want to like graph that then, it would be the opposite of where it was pointing before because of that negation factor. Now, thinking about adding two vectors together, again, we are just combining the A components and the B components. So that's going to happen as well when it comes to our graphs here with vectors v and w. Because the thing is, vector v, again, we know is at 3, 4. So if we take 3, 4, and you take 3 and then add to it vector w, which again is negated, we would have 3 plus 2 for component A, and then 4 and -5 for B, for a final resulting vector of 5, -1 on that. So the idea of this is, again, you're adding that negative. Essentially what it turns into is then you could also think about as you are subtracting, for instance, that value. So 3 minus negative 2 is the same thing as 3 plus 2, 4 minus 5. So again, that works out as well if you don't like the idea of the additive inverse. So we see again a couple more examples down here. This first one, we want s minus t. So in this case, we would take s and then minus the t. So negative 2 minus 1, and then 2 minus negative 4. So our resulting vector would be negative 3, and then 2 plus 4 is 6. On the other one, we are going to go the opposite direction. So we're going to do 1 minus negative 2, negative 4 minus 2. This time our resulting vector ends up being 3, negative 6. So unlike vector addition, vector subtraction, you want to be careful because you're not going to necessarily, s minus t is not the same thing as t minus s, so order is important. The last type of problem then we are going to talk about is our scalar multiplication. In this case, think about it's almost like distribution, because if you're doing 3 times your vector, it's almost like you're adding it together 3 times, aka multiplication, distribute that 3 through. So we see on this one, vector v is negative 2, 4. So we would distribute through essentially a 2 to both pieces. We end up with negative 4, 8 as our resulting vector. Or maybe you are distributing through vector w a negative 2. So you're not only taking the additive inverse, but you're also expanding it by 2. So you end up with 6, 2 would be your resulting vector on that one. All right, thanks everyone for watching. We'll work more with these in class.